Good morning, ladies and gentlemen. Welcome to today's lesson on Newton's second law. This is our very first video of our second unit, dynamics. So we will have just finished up with our kinematics unit. And now remember, kinematics, ladies and gentlemen, is the study of how objects move. So whether they're going to be moving in accelerated motion or a constant motion, or if in the case of projectile motion, uniform on one plane and accelerated on another. That's how they're moving. Whereas in dynamics, well, it's why does all of that happen? Why do objects move the way they do? And the answer to that is going to be based around forces. Now, not the Force as in Star Wars, as cool as that would be. We're not going all Darth Vader or going all Luke Skywalker in this unit. Sorry, guys. But the physics definition of a force is either a push or a pull. Okay, so I've got a tea mug. There's no tea in here, just a mug. I don't drink coffee, so it's a tea mug. All right, so here's my mug, and I'm going to apply a force to said mug. Okay, well, here I am pushing on the mug. Here I am pulling on the mug. I have applied a force in both of those cases to said mug. Here I'm pushing on the mug, but is it moving? No. I am pulling on the mug, but is it moving? No. So in all of those cases, I have applied a force to the mug. However, just because you apply a force to an object, it doesn't necessarily mean it's going to be moving, okay? And just because you apply force to an object, it doesn't mean that it's going to be accelerating either. So I'll talk a little bit more about that in a bit. Now, our unit is newtons. Sound good? All right. And ladies and gentlemen, super important here. Force is a vector, okay? It has both direction and it has magnitude. So add that to your list of things to remember, ladies and gentlemen, because you need to know that. When I ask you for a net force in a question, and I say, what is the force of this? I want a direction with that final answer. Cool beans? Cool beans. So let us scroll down a bit. Okay. So ladies and gentlemen, one of our big focuses and concepts in this unit is going to be on net force. Now, what does the word net mean? It implies the total. So for those of you who have jobs, on your pay stubs, I think they're all digital these days, but you'll have your employee account and you'll get your digital pay stub. And as you're looking at your pay stub, you will see your gross pay and your net pay. Well, your net pay is the sum of your earnings and the deductions. So the deductions would be like adding a negative. So your net pay is what you take home. It's the total of everything, including the positive money as in what you earn, and the negative money is in the deductions. So taxes, or if you work for a union dues, benefits, whatever. Okay, so all of those would be deducted from your pay. So the net pay is what you're left with in the end. The same idea here. The net force. Now the computer messed up all of my vector arrows, turned them into wonky U's. So I'm sorry. These are all supposed to be vector arrows, not wonky W's. So the net force is defined as the sum or total of all forces that an object is experiencing at a single point in time. Okay. So, for example, I am holding my mug. Now, as I am holding this mug, what force is acting on it downwards? Force of gravity. Absolutely. So the force of gravity is pulling downwards on this mug. Okay. Now I am applying a force to the mug. by holding it here. I am applying a force upwards. So right now, do we have a net force? Well, sure. But because the object isn't going anywhere, the sum of all of the forces are going to add up to 0 because the mug isn't moving. Now, if I dropped the mug, it would break, which I don't want to do. But if I dropped it, we would have a net force going downwards. Okay? Okay. So thinking about that mug example, we have, I give you both examples of an unbalanced and balanced forces. So ladies and gentlemen, an unbalanced force, so an unbalanced net force, it means that you are going to have more force on one part than another. So in the case of me dropping the mug, we would absolutely have the force of gravity being greater than any other force on it. So the mug would accelerate at 9.81 meters per second squared towards the ground. So if you have an unbalanced force or a net force that is non-zero on an object, you are going to have the object accelerate. So an unbalanced net force, and I want you guys to write this piece down, please, is where F net is not equal to 0 newtons. Okay? So that is particularly important. In order for acceleration to occur, you have to have a net force. In order for a net force to be applied, the object needs to be accelerated. Okay? Okay. So, ladies and gentlemen, an unbalanced force is going to cause an object to experience a change in velocity. Well, what happens when an object's velocity changes? Acceleration. On your data sheet, sadly I don't have a data sheet with me today. You'll see it in the dynamic section of your data sheet. You will see this equation here. Okay. Now, this one is often used, but I personally really like using this version of the equation better. I don't know why. Okay, maybe because it's linear, makes life easier. So this is the rearranged version of the equation. So F net equals ma. This is the equation based on Newton's second law. This is Newton's second law equation. So whenever we say Newton's second law, we mean F net equals ma. All right? Okay. So, ladies and gentlemen, F net is the net force acting on the object. Okay. We're going to be talking more and more about net forces 2 videos from now, where we start doing our force diagrams and that type of thing. Okay? All right. So, M is the mass of the object in kilograms, force is in newtons, and acceleration is meters per second squared, as always. Excuse me. Cool beans? Cool beans. All right. So, ladies and gentlemen, Newton's second law of motion. Remember that Newton's second law of motion is F net equals ma. All right? It is going to be referring to any time you have any unbalanced force, unbalanced net force that is going to make an object accelerate. Okay? All right? Now, when an object experiences no acceleration and is either moving at a constant speed or is at rest, there is balanced forces acting on the object. When an object has balanced forces, what does that mean about our F net? It means F net is 0. Okay, remember the mug example? All right, now while I'm holding this mug, there are balanced forces. The force of gravity is going this way. I am applying a force that's going this way. All right? So therefore, the mug is stationary. All right, so that is an example of balanced forces. So let's look at the mug again. Now, right now, if I'm going to be applying a net force, the mug will start slow and then speed up as it moves. Whereas, if I'm just going to be moving the mug at a constant speed, that is a balanced force. Notice how the mug is not accelerating here. The force of friction, which is slowing the mug down, is going to be equal to the force that I am applying to that mug. So unless the mug is accelerating, there is not a net force. Sounds good? Okay. So, ladies and gentlemen, super important, that actually is going to come into play to impact your calculations. So we will talk about that a little bit later. All right? Okay. So let's talk about some vector arrows, excuse me. So when a net force is going to be applied to an object in the same direction that the object is moving, it's going to speed up. Okay, so this would be the same as your positive acceleration. So let's use our red arrows in order to represent velocity, and let's use blue arrows to represent our F net. Okay, all right. So if you are going to have an object that is already moving this way, and I am going to apply a net force acting in that same direction, you are going to get positive acceleration. You are going to have an object speed up. Okay? That's where you are going to have an object speeding up. All right? Well, let's say we have an object that is moving this way, and we are going to apply a force going in the opposite direction to where it's already moving. The object is going to slow down. Okay. Now, what is now the formal term for deceleration? Negative acceleration. Sounds good? Okay. So let us move along to graphing. All right, so there's a couple different ways that we can represent Newton's second law graphically. So the first piece that we're going to do is we are going to look at the relationship between our F net and our acceleration. Sounds good? All right. So the acceleration, or change in velocity, is proportional to the net force. Okay. Now, the formal mathematical definition of proportional is when the manipulating variable increases or changes, the responding variable changes the same way. So, therefore, increases as well by the same factor. Okay. So, let's represent this graphically. Let's say we're going to go F naught versus acceleration. So my F naught is going to be here on the y, that's my responding variable. My acceleration on the x would be my manipulated variable. So F naught equals ma. Well, right now we are going to be assuming that mass is constant. Okay, mass would be a controlled variable, something that you keep the same. In this case, I would be changing my acceleration because it would be my manipulated variable. So because this is constant, I can leave it out and rewrite this as my F net is proportionate to acceleration. So this fish means proportionate. Okay, so if I'm going to double my acceleration, that means my F net would wind up having to double. So you're going to wind up with a graph that is going to be linear like this. That's not the nicest of lines. Let me redraw that. It's really hard to draw straight lines in the program I'm using. There you go. We're going to assume this is a straight line because apparently I can't draw a straight line close enough. It's going to have to do. Okay? All right. So what this means, as your F net increases, your acceleration is going to increase. Okay? Sounds good? Okay. So let us look at another way that we can also look at this graphically. So as well, Newton's second law, the mass is also proportional to the net force acting on an object. In this case, the acceleration is going to be the same. All right, so remember, F net is equal to ma. In this case, ladies and gentlemen, we are going to be comparing our F net and our mass. Okay, so F net not equals mass versus mass. So my F net is going to be my responding variable here, and this is going to be the mass. So think about a vehicle. How many of you guys have driven a small car before? Drove a small car for years, a little Honda Civic, standard transmission. It was a beauty. Love driving standard because you can get the torque exactly the way you need it for that scenario, and you can use your gears for acceleration and use them on hills. Oh, it's great. You can even slow down without your brakes quite nicely on really icy roads in standard. Awesome. So versus an F-150 or a pickup truck. Some of you guys have driven a pickup truck. So drive now. So that or the Subaru. So my husband and I have both the Ford F-150 and the Subaru. So with the F-150, if I'm going to accelerate a little car, say my old Honda Civic or my current Subaru, versus my F-150, and then both want to accelerate them, I don't know, 3.5 meters per second squared. Just say. If I want to have equal acceleration between the two vehicles, the F-150 and the Subaru, which object am I going to have to apply the most force to? The F-150. Because its mass is larger. There's more of it. So in order to get it to accelerate the same as a Honda Civic, you're going to need to apply more force. Which is why big trucks do not have the same fuel efficiency as smaller cars. Because you need more gas to create more force to get the same type of motion out of them. So one thing I did love about the Honda Civic is fuel efficiency. $40 for a tank of gas, and it would get me the same distance that $110 worth of gas gets me in my F-150. Hello? Excuse me. Although it's you can't tow things in an F-150 or in a Honda Civic. So, and I drove a ton of gravel roads in that Civic, but so much easier to drive gravel in a pickup truck. Okay? 4x4, get you out of the mud. It's good. All right. So, ladies and gentlemen, back to the math and the graphing behind your Honda Civic and F-150. So we're going to get the acceleration to be the same. So that means the F net required to get equal acceleration out of object is going to be proportionate to the mass. So in order to get the same acceleration, when you increase the mass of an object, that F net is going to increase. Okay. Sounds good? Good. So if you double the mass and the acceleration is the same, the F net required to move that object to that same acceleration is going to double. They are directly proportionate. Sounds good? All right. So, ladies and gentlemen, let's get that written down. So, as your mass increases, the F net required is also going to increase. Sounds good? Cool beans. There's also a couple of different ways that you can graphically represent an unbalanced force. So, when are we going to have unbalanced forces? When an object is accelerating. Okay? So, any graph that is showing accelerated motion, dropped an I there, you are going to have an unbalanced force. So, what we have here, let's go a position versus time graph. So here is our position, there is time. Think back to kinematics. What pattern of graph is that going to be? Good. Okay. So, ladies and gentlemen, how else can we represent this? Well, we can go velocity versus time graph. We can have velocity here. We can have time here. Now, the problem with this pattern, can we really do a lot of easy math with it? No. We'd have to go through a bunch of graph straightening stuff, and we're not doing that until physics 30. So we're not going to worry about dealing with that. Well, if you have a distance versus time graph, we can get a velocity versus time graph. That's much nicer. That is, once again, a wonky line. I can't seem to draw straight lines here. Close enough. So, ladies and gentlemen, what can I do mathematically in order to get the F net off of this? Slope. So remember here, our slope is equal to our change in y over our change in x of the line. Well, here, our change in y is velocity, and over our change in time on the x, well, that would give us our acceleration. So in this case, our slope equals the acceleration. Once you have the acceleration, if you have the mass, you can find F net. Cool beans? Cool beans. Another way that we could also represent accelerated motion is our acceleration versus time graph. So essentially, any of the graph patterns that we've looked at previously that show acceleration can also be used to help with F net. Sounds good? All right. So let us look at our calculations. So we've got two that are fairly straightforward here. And yes, they're pretty much the same, but there is only actually like two words and one letter, or one number, that are different here. Okay, there's a trick to it. So ladies and gentlemen, calculate the magnitude. Now this is a key piece. This is a really nice thing. Anytime I say magnitude of a vector, that means I don't want the direction in that question. I just need the value. Often when I say calculate the magnitude of the force or something like that, it means that I have not given you enough information to calculate the actual direction. Sounds good? All right. All right. So, ladies and gentlemen, just the value, no direction. For this, I don't want a direction because I said what is the magnitude. All right, no direction. So calculate the magnitude of the net force. So we're trying to find F net. Acting on a 1.5 kilogram toy airplane. Traveling at 4 meters per second. Well, that's its velocity. So ladies and gentlemen, F net equals MA. What's the catch with this question? Have you guys found it? There is no acceleration. This is constant speed. It's not changing. Therefore, there is going to be no acceleration. Acceleration is going to equal 0 meters per second squared. If acceleration is equal to 0 meters per second squared, what's our F net? 0. So, there we go. F net is 0 newtons because the airplane is not accelerating. Sounds good? Easy enough. That is going to be a concept that comes up again and again and again throughout this particular course. This unit, or actually this course in general, dynamics comes up again in future units too. So when we have our lovely statement that is saying uniform motion, that means your F net is going to be 0. That is going to impact future calculations, so keep that in mind. Sounds good, guys? All right. Okay. So let's redo the same question here, except we have calculate the magnitude of the net force. So we're still having to calculate our F net here. Okay. So F net is our question mark on a 1.5 kilogram toy airplane. And when it is accelerating at 4 meters per second squared. So in that case, we have a value for A. Okay. And note the units, meters per second squared. We are accelerating here. So 4 meters per second squared. Sounds good? All right. So in this case, we can absolutely calculate our F net. F net equals MA. Plunk in your numbers. 1.5 kilograms multiplied by your 4 meters per second squared. And you are going to get a lovely value of 6 newtons. Now, sig digs. I said magnitude, so I don't want direction. 2 sig digs here, 3 sig digs here. So 6.0 newtons. Magnitude, so no direction. Sounds good? All right. So that's just kind of those two questions are a nice warm up to get you used to the concept of when you're going to have an F net and when you're not. All right. Okay. So let's go and look at some next questions here. And some of these letters traveled down into the next page. Okay, so let's look at question 3. A 22 kilogram object, all right, we have the mass, decelerates uniformly. Okay, so we know we're going to be slowing down here, so that means our A is going to be negative. Okay, and goes from 2.5 meters per second west. Okay, that's our VI. To a stop. Okay, so VF is going to be 0 meters per second in 8.7 seconds. Okay, what is the net force acting on the car during this acceleration? Okay, so ladies and gentlemen, we're going to need to decide what direction we want to be positive here. I am going to choose to make west positive because it's going forward. Okay, so sounds good? All right. Well, I need my F net. Well, my F net equation is MA. Well, how am I going to get my acceleration? You said VF minus VI over delta T. You are correct. So that's the first thing I got to do. And that's the second thing. So I will calculate my acceleration first. I'm going to choose to make west positive and east negative. Okay? Okay. So my 2.5 is, whoops, I'm going to write out my equation first. So VF minus VI over delta T. Acceleration is going to equal my VF of 0 minus my VI of 2.5. It's going to give me negative, which is what I want, divided by my time of 8.7 seconds. That is going to give me an acceleration that is going to be negative 0.2873 ... meters per second squared. Now, I want this to be negative. Why do I want this negative? Because I'm slowing down. Okay? I want to have negative acceleration when an object is slowing down. So I now need to find my F net. I have the mass of 22 kilograms. And then I'm going to take this whole value, no rounding now, use the whole value in your calculator, multiply those together. I'm going to wind up with a numerical value of negative 6.3218 ... Sounds good? Good. So with the F net, I'm going to write my final answer underneath where I've got more space. Okay, I need sig digs, I need units, and I need direction. So I come up here, 2 sig digs, 2 sig digs, 2 sig digs. So 6.3, okay, because I look back here, this is going to round to 3. And newtons, and it's negative, so that means my force is going to be going east. Okay, because I made west positive. Sounds good? Okay. If you guys would like, you are welcome to make east positive and west negative. You're more than welcome to do that. It's if that makes more sense to you, do it. Okay, you are still going to wind up with the correct answer in the end of 6.3 newtons east. It's just your answer would be a positive 6.3 instead of a negative. So it doesn't really matter, but I always like designating forward as positive. Sounds good? All right. So we got one more question and then we're done the lesson for today. Yeah, these particular letters keep wanting to travel with us. Okay. Excuse me. Sorry, I just got a cold. It's not COVID, I promise. It's just a cold. Which is why I am not at work today and filming this at, what is it, like 9:30 on a Tuesday or something. Yeah, I got a cold. My COVID test was negative. I'm all good, but I still have to stay home. I wish I was at school teaching you guys. Miss you guys already. Okay. So Canada's motor torpedo boats are patrolled the English Channel during World War II. World War II history is pretty cool. They got some of the pretty neat machines from that era. So when the engines of the NTB exerted a force, okay, so we got a force, and it's a net force, not just any force, it's the net force. F net is 340. Now watch your units, that's kilonewtons. Okay. On an MTB with a mass of 5.5 times 10 to the 4 kilograms, the boat could accelerate from rest. Okay. So from rest, so VI is 0 meters per second to 50 meters per second. What is the distance that the MTB would travel as it reached the 50 meters per second. Now, distance is scalar, so that means I do not want a direction with my answer. Sounds good? All right. Okay. Well, ladies and gentlemen, let's plot our course for this question. It's a pun. Laugh at my pun. Because we're dealing with boats. Plotting the course. Anyway. It's a pretty lame joke. Yeah, let's be honest. But I guess you're used to my lame jokes by now. So, ladies and gentlemen, we have an object that is accelerating. We know this because it's going from VI to VF, and we know that we have a net force being applied. So, what we've got is F net M. When we have these two, what can I calculate? I can get acceleration out of this. Once I have acceleration, VI, VF. Can I get distance? Of course. So my first thing is going to be my F net equals MA. And then I'm going to use that to calculate my acceleration. So, but what do I have to do with my mass first? I'm just going to put in 340, right? No! I need to convert these units. Okay? I'll write that a bit neater. Using your data sheets, you will see that kilo is times 10 to the power of 3. So you are going to get 3.40 times 10 to the power of... I'm having a Monday here, guys. And let's not write it in scientific notation. All right. It's not Monday, it's Tuesday, but, you know. All right, I just added 3 zeros. It should be 5. 1, 2, 3, 4, 5. Yeah. So 3.4 times 10 to the power of 5. You can do that too. So that is going to be our force in newtons. Okay, well, we want our acceleration, so we're going to use the rearranged version of that equation. So acceleration is equal to F net over mass. And our F net is our, 3.4 times 10 to the power of 5 newtons. Or you can write it like this. Either way, that's fine. And our mass is our 5.5 times 10 to the power of 4 kilograms. And we're going to wind up with acceleration of 6.18 repeating meters per second squared. Leave all those values in your equations. Now, what equation do we want for our next step? We have acceleration, we got VI, we got VF. We're trying to find distance. If you said VF squared equals our VI squared plus 2AD, you would be correct. So, ladies and gentlemen, VI is equal to 0. Okay, so our VF squared is going to equal 2AD. I am going to square root both sides to cancel out that square. So my VF is going to equal root 2AD. I'm going to come back up here for more space. So I'm going to plunk my numbers into my equation. So 2 times my acceleration of 6.18 repeating using all those digits from your calculators. Did you guys see what I did wrong? I rearranged my equation wrong. I am really sorry, guys. It is such a Monday on a Tuesday. I hope you guys caught that and were wondering what the heck. You're like, Mrs. Bray, what are you doing? I hope that's what you guys were thinking. Okay. So, I like when you guys catch the silly things that I do. It's good. It shows you're thinking about stuff. I mean, we're all human. Screwing up is what we are good at, right? Exactly. So, if you ever screw up, don't ever feel guilty about it. You just fix it and carry on because, apologize, fix it, and carry on. What else can you do? Okay. So VF squared is equal to 2AD. We're trying to find D. So I'm going to divide both sides by 2A. Now we have VF squared over 2A is going to give us our distance. That's more like it. So our VF is 50. We're going to square that. We're going to divide by 2 times 6.18 repeating. Using all those digits from your calculator. All right. Once you plug in your equations, plug your numbers in your equations, put that in your calculator. You're going to wind it with 2.2.205 ... Okay. I asked for distance, not displacement, so that means no direction, please. And we are going to now look at our sig digs. 3 sig digs at 2 sig digs. Because I want 2 sig digs, we're going to put this in scientific notation because there's 3 numbers here before that decimal. So I'm going to look back here. Well, this is going to round down. So 2.0 times 10 to the power of 2 meters. All right. Okay. No direction because I said distance. All right. So, ladies and gentlemen, I hope you guys enjoyed the video. We got practice problems here for you out of your lovely workbook, so give some of those a shot. I recommend doing a decent number of these. Make sure you are fully comfortable with them before you go on. And in your notes, I've also got a bunch of other practice problems here for you to do. And of course, more graphing questions, your favorite. And then we've got questions to go with that. All right. Okay. So I hope you guys have a good rest of your day and no fires, injuries, or explosions. Talk to you guys later. Bye. No, I can't turn it off. You think with the number of videos I've made by now that I could turn off this silly thing. There you go. Talk to you guys later. Bye.